Hey there, Iron Designer here. So once in a while we get questions from students on how to solve engineering problems. And I thought this was a pretty interesting one because it requires a lot of knowledge from different subjects all being put together to get the final answer. So the problem basically asks if you hit a slugging wrench with a hammer at 12 feet per second and the hammer weighs 5 pounds, then what does the diameter of the wrench need to be? So that's kind of like a stress analysis problem combined with an energy problem. So many times in engineering, especially here at Iron Designer Studios, you need to attack a problem from many different sides, and then you have to do substitution in the equations to create your own equation, and from that equation you need to solve for a particular variable, and then you verify your answer. So that's what's going on in this homework problem. Now, even the engineers that work at Iron Designer, they start off by making a sketch. So you have kind of a visual or graphical representation of what your problem is going to be, or maybe you'll come up with a CAD drawing or some kind of 3D solid model, because visualization is one of the best ways in order to understand a problem and to be able to identify the different components and which parts are moving, which are fixed, where's the deflection at, where does the energy come in from, how does the energy get dissipated. And so it's always best to start off with some kind of a diagram or a sketch. So in this problem, we decided to start with the hammer because it's sort of the moving part. It has the kinetic energy. And we know from basic physics that energy is neither created nor destroyed, but it can be changed from one form to another. So we understand that the kinetic energy, once it impacts on the wrench, it's going to be changed into potential energy, which is going to cause a deflection in the arm of the wrench. So that's how we decided to set this problem up. So first we computed the total kinetic energy of the wrench and how that total kinetic energy of the wrench is going to be imparted into potential energy, in other words, mgh. And we do our substitution. We know that there's deflection, we know there's stress, and we know the general dimensions of the wrench. So we begin looking for formulas that have all those attributes built into them. So all we have to do is do substitutions, do combinations, solve for the particular variable that we're looking for. Ultimately, it's going to be D, which is the diameter of the wrench arm. And that's what we're trying to get at the very end of this puzzle. Now, when you're an engineer, you have to have the ability to combine various ideas and concepts together, because rarely is a problem going to be put in front of you that's just going to be like open up the textbook, finger down to a single formula, plug, chug, send the answer back. That's almost never going to happen. What usually happens is that you have multiple ideas all working together simultaneously, and you need to solve multiple equations at the same time. So in this part of the problem solving, now we're looking at the potential energy problem inside the wrench. So we've taken the hammer, the kinetic energy, and we've transferred the kinetic energy into potential energy. We've deflected the arm of the wrench, and now we're looking to see how does that energy turn into stress through deflection and ultimately through the diameter of the wrench. For example, another type of problem might be combustion energy turning into thermal energy, turning into frictional energy, turning into mechanical energy, turning into some kind of a power equation, then turning into some kind of an electrical equation, then turning into some kind of gear reduction equation, then turning into some kind of ultimate motor horsepower equation. Now, as with all studies, you're going to get to sort of a mid-step. And what you want to do in the mid step, which is usually your derivation step, where you're deriving or you're introducing a formula, but you're not really sure where the formula comes from. So you want to break down the various variables into subvariables and maybe even break them apart even further. Like, for example, in this equation, you have m squared times L. And people would say, where did the m squared come from? Well, you know that m, moment, is force times distance, which is px. So you would have px times x. So now you substitute px for m, and you're going to have m squared L. So you have to show your mid-step solutions as well. So now here in this screen is a perfect example of solving for the variable that you want. And I'm going to leave it up to the student and the viewer to do the derivation and compute backwards how we pulled this equation by combining other equations and doing other substitutions. But what I did do here is I broke it down a little bit so you can see what all the variables are. And if you want to prove it to yourself, you can go in and do a dimensionless solution, which means just plug in the dimensions, inches, seconds, pounds, things like that, and see that it all solves out by cancellation into inches. That's actually another secret way that engineers solve equations, is by doing them dimensionlessly and just solving for the dimension that they want, just to verify that their equations make sense. It's like a sanity check way of double checking that your substitutions and your combinations of equations was done correctly to maintain all the units till the end. Because you don't want to think you're solving for inches, and at the end when you solve for all your dimensions, you've got inches per second or something like that. Now in the end, as you will see as an engineer or even a junior engineer, by now looking at the solution, you should be raising your hand and calling out a red flag and saying, but sir, your answer is 2.07 inches and the actual wrench diameter is 2.0 inches by measurement, or maybe even less. Maybe it's 1.99 or 1.98. So at that point, you need to be questioning your results or questioning what your input data was, because if your results are outside of the parameter of the physical wrench or the physical component, at that point, that's when you need to do another analysis and run some kind of additional stress analysis. Maybe it's not 40,000 psi like we put into the assumptions at the beginning of the problem. Maybe it's really 39,000 psi. Or maybe it's not 12 feet per second, maybe it's 11.5. So now you as the engineer, as the analyst, as the technical analyst or the data analyst, is now the spotlight is on you to make a determination as to how you want to proceed. Because maybe you cannot reduce the velocity of the hammer, maybe you cannot reduce the mass of the hammer, but also you cannot increase the diameter of the wrench. So you kind of face this dilemma and you have to come up with your own conclusion as a professional engineer. So what I've done on the next slide is, let's say it's not a wrench, let's say it's a simply supported bar, but all the other parameters remain the same. Now I want you to take the equation for the simply supported bar and solve the problem for diameter as we did previously, just for you to have a homework problem to work on. So thank you very much for spending time on the video, and this is Iron Designer. We are out, and if you have any questions or problems you want us to solve for you, please put a link in the comments below. Thanks.